Number 1. The Sirena Deep Yellow Mats, the 2019 5 Deeps anomaly. Submersible lights cut through absolute black water at roughly 10,677 meters below the surface. That is close to 10.7 kilometers of water above your head. The location is Sirena Deep, the second deepest known point in the Mariana Trench. The pressure outside the hull sits near 107 to 108 megapascals. That is more than 1,000 times the air pressure you breathe right now. And in this place, where light has not reached for the entire history of the ocean, the lights of the submersible swept across something nobody could identify. The visual was strange. Yellowish, filamentous, mat-like material was clinging to hard substrate. Not soft mud, not sediment. The structures coated rock or talus where currents swept past. They appeared to quiver as the vehicle approached. The team described them as novel, which in scientific language means they were not formally identified as any known species. No clean match in the catalog, no standard reference image, just yellow strands holding to stone at the edge of full ocean depth. For most of the 20th century, the deepest trenches were imagined as food-poor deserts. The model was simple. Sunlight cannot reach there. Photosynthesis cannot happen there. Therefore, the trenches must be fed only by debris falling from the surface. Marine snow drifting down, the occasional dead fish or whale, a slow trickle of carbon. Under that picture, you should not expect dense life clinging to bare rock. You should expect mud and silence. The Sirena observation does not fit that picture cleanly. A possible explanation involves chemolitho-autotrophic systems. That phrase sounds heavy, but the idea is direct. Some microbes use chemical energy instead of sunlight. They oxidize sulfur. They cycle iron between oxidized and reduced states. They consume methane. They feed on hydrogen produced by reactions between rock and seawater. Any of these metabolisms can support a microbial mat. Yellow color can come from biological pigment, from sulfur-rich chemistry, from iron staining of the surface, or simply from how the camera lights interact with translucent material in pure black water. Here is the catch. Nobody sampled it. The mats were observed but not collected. That distinction is the heart of the mystery. Without a sample, there is no microscopy, no DNA sequencing, no isotope analysis, no mineral chemistry. The knowledge is not lost in a historical sense. The records exist. The footage exists. The knowledge is physically inaccessible because the material was never brought to a laboratory. You can look at the screen all day and still not know what is on it. The mainstream interpretation treats the structure as a microbial mat or a chemically mediated biofilm. A more historically grounded view holds that this is part of a wider pattern, that trenches contain hidden chemosynthetic niches missed by sediment-focused sampling. A more speculative reading suggests that the deep biosphere may express itself in ways unlike any shallow vent system, with metabolisms not yet characterized. That last reading remains unverified. It's interesting, it is not proven. Future missions will need sterile samplers, close-range imaging, and chemical probes that can read the local fluid before disturbing it. Comparison sites already exist. Microbial mats grow near cold seeps, near hydrothermal vents, and near serpentinite systems that release hydrogen-rich fluids. Those mats can be tested. The Sirena observation has not yet joined that catalog. The unsettling part of this story is not a creature. It is the fact that something was visible, was filmed, was described in scientific reports, and still could not be explained because it was never touched. So if life can hide that easily inside a video frame, what does the trench sound like when nobody's watching at all? Number 2. The slowdown. The 1997 Hadal hydrophone anomaly. On May 19, 1997, hydrophones across the Pacific recorded a long descending sound. It lasted about 7 minutes. That duration alone is unusual. Most short ocean noises are exactly that, short. A pulse, a click, a whale call, a quake. 7 minutes is a structure, not a moment. The signature was a downward sliding frequency, falling in pitch as the recording continued. That falling tone gave the event its public name, the slowdown. The estimated source was located near 62 degrees south, 60 degrees west, off the Antarctic Peninsula. That is far from any of the deepest trenches. So why does it belong in a documentary about Hadal mysteries? Because the deep ocean is acoustically continuous. Sound travels through it efficiently, especially through the deep sound channel where temperature and pressure focus low-frequency waves. A noise generated in one part of the basin can be detected thousands of kilometers away. The trench environment is part of that same listening room. For a long time, the slowdown circulated online as an unsolved deep ocean signal, often paired with the more famous bloop. The two events are separate, different signatures, different interpretations, different science. The bloop was eventually attributed to icequake activity. The slowdown has its own best explanation, and that explanation is iceberg grounding. Picture an iceberg with a deep keel scraping along the seafloor. As the keel drags, friction builds. The iceberg slows. Vibrations radiate outward. The frequency drops as the motion slows. That descending tone matches what the hydrophones recorded. NOAA's acoustic catalog identifies iceberg grounding as the most probable source. Similar sounds have been recorded repeatedly in polar oceans since. There's a reason the mystery survives in popular memory. The original sound went viral. The correction did not. A descending alien tone is more shareable than a paragraph about ice keels and deep sound channels. So the myth lasted longer than the science. No known animal could produce basin-scale acoustic energy for 7 straight minutes. Whale calls are loud, but they do not match this profile. Earthquakes are short, volcanoes have their own signature, the remaining candidates are physical, not biological. Ice friction works. The phrase to use here is once unexplained, not still unexplained. The historical context matters. Cold War hydrophone networks made the deep sea audible to humans for the first time. Those networks were built to track submarines. They ended up tracking earthquakes, ice breakup, volcanoes, whales, and human shipping traffic. The ocean had always been making these sounds. We just had no microphones until the 20th century pushed them down there. The mainstream theory holds. Iceberg seafloor friction created the descending signal. The historical reading frames this as a moment when deep ocean acoustics revealed that ice, not animals, can sound like a monster. The fringe reading suggests an unknown source, biological or geological, but no evidence supports that view. The frightening element here is not what the sound was. It is what the ocean is willing to make when nobody is listening. Dead ice scraping rock under darkness. And that opens a question. If the trench environment can swallow sound, sediment, and chemistry without anyone noticing, what happens when humans send their own machines down to look? Number 3, the robot graveyard, Kaiko and Nereus. The trenches contain more than organisms and sediment. They contain the remains of failed exploration machines. 2 stand out, both lost during operations meant to extend human reach into full ocean depth. Each loss tells you something about the limits of engineering at that depth. Kaiko was built by JAMSTEC, the Japan Agency for Marine Earth Science and Technology. It was a remotely operated vehicle rated for full ocean depth. That rating is not a marketing line. It means the entire pressure envelope, every joint, every cable connector, every electronic housing was tested to survive at the bottom of the deepest trenches. Kaiko did the work it was built for. It reached Challenger Deep, it enabled some of the earliest direct Hadal sampling, returning sediment, water, and biological specimens. In May 2003, Kaiko was lost. The location is sometimes summarized as the Japan Trench, but the precise loss occurred off Shikoku at a depth of approximately 4,675 meters, not cleanly inside the deepest section of the trench. The cause was a secondary cable failure. The cable that connected the vehicle to its support system separated. With that link broken, Kaiko was no longer recoverable. Cable fatigue in deep-sea operations is a slow problem. Repeated bending, repeated tension cycles, exposure to pressure, and long contact with seawater all degrade aramid fibers and electrical conductors. A single weak point eventually fails. Once a vehicle is untethered at abyssal depth, recovery becomes nearly impossible. There are no rescue teams that can reach those depths quickly. There are no surface markers strong enough to track a drifting hull through the dark. The vehicle is gone in operational terms within minutes. The second loss is Nereus. Nereus was built by the Woods Hole Oceanographic Institution. It was a hybrid design. It could operate as a remotely operated vehicle, tethered to a ship, or as an autonomous underwater vehicle running independently. It was rated for full ocean depth. On May 10, 2014, Nereus was lost in the Kermadec Trench at approximately 9,990 meters depth. Pressure at that depth approaches 16,000 pounds per square inch. That is enough to crush any weak point in the pressure system instantly. The likely cause was catastrophic implosion, indicated by floating debris recovered at the surface. Implosion at that pressure happens faster than a human can react. The hull goes from intact to destroyed in milliseconds. The Woods Hole team treated the loss as an extreme pressure system failure, the kind of event that engineering only learns from after it occurs. The mainstream conclusions are direct. Kaiko failed by cable separation. Nereus failed by pressure implosion. The historical reading places both losses inside a long list of trench engineering failures. Each one taught the next generation of designers what not to repeat. A more speculative view considers trench currents, collision with the seafloor, or unknown geologic disturbance. But the evidence for those alternatives is limited. Modern full-depth vehicles now require pressure-tested housings, multiple fail-safes, acoustic releases that drop weights when commands fail, and redundant communication systems. Each design choice carries the memory of a previous loss. The trench is not a passive backdrop. It is a mechanical execution chamber governed by pressure, fatigue, and material limits. Two national programs lost their flagship machines to the same environment. So what is in that environment that makes it worth the risk to keep going back? Number 4. The South Chamorro serpentinite mud volcano. On the Mariana forearc above the subducting Pacific plate, a chalk-white volcano sits on the seafloor. It does not erupt lava. It pushes out cold alkaline mud. This is South Chamorro, a serpentinite mud volcano. It is part of a wider system. The Mariana forearc contains many large serpentinite mud volcanoes, some tens of kilometers wide and rising kilometers above the surrounding seafloor. They are not classical volcanic cones. They are chemical structures. The process behind them is straightforward in outline, even if the chemistry is dense. The Pacific plate slides beneath the Mariana forearc. As it goes down, it carries water locked inside hydrated minerals. That water rises through faults into the overlying mantle wedge, where it meets ultramafic rock. The reaction between water and ultramafic rock is called serpentinization. It produces serpentine minerals, the mineral brucite, hydrogen gas, and strongly alkaline fluids. The fluids and altered mud rise through the crust until they reach the seafloor and pile up. The chemistry is unusual by surface standards. Fluids at South Chamorro can reach a pH of about 12.2 to 12.5. That is comparable to caustic industrial alkalinity. Methane is present. Hydrogen is present. The white surface comes from brucite-rich, pale serpentinite mud coating the seafloor. The whole system reads like a cold chemical volcano running on rock plus water rather than magma. Drilling has provided direct access. Ocean drilling program. Hole 1200C was installed at South Chamorro and used as a borehole observatory. Experiments at the borehole reported fluid discharge on the order of thousands of liters per day of altered fluid flow. That is not a still pool. It is an active chemical engine. Life clusters around it. Chemical energy replaces sunlight. Known fauna include gastropods and snails, mussel-like bivalves, crustaceans, and microbial mats. The animals depend on microbial communities that use the chemistry of the rising fluids. Hydrogen and methane are valuable energy sources for the right microbes. Those microbes form the base of a food web that does not need a single photon from the sun. This kind of system was hidden for a long time because it does not match either standard model of seafloor life. It is not a normal volcano. It is not a classic black smoker hydrothermal vent. It sits between categories. The mainstream theory holds that serpentinization generates hydrogen-rich, alkaline fluids that sustain chemosynthesis. The historical research view treats forearc mud volcanoes as windows into subduction zone chemistry, places where deep processes reach the surface in slow motion. A more speculative reading suggests that systems like these resemble possible habitats on Europa or other ocean worlds where rock and water meet under ice. Direct equivalence is unproven, but the comparison is part of why South Chamorro is studied seriously by astrobiologists. The point that stands without speculation is simple. Life can innovate from basic ingredients: water, rock, heat, pressure, chemical imbalance. Where any of those exist together, biology has a chance. The trench wall is not a dead place. It is a working chemical system. If life can build itself from rock and water in a place like that, what else has the trench been quietly recording without anyone watching? Number 5. The Hadal Carbon-14 Reservoir. During the Cold War, atmospheric nuclear tests sent radioactive carbon into the sky. Decades later, that same carbon turned up inside animals living at the bottom of the deepest trenches on Earth. The path between those two facts is a story of how the surface and the Hadal zone are connected. Carbon-14 is a radioactive isotope of carbon. It is naturally produced in the upper atmosphere by cosmic ray interactions with nitrogen. Living organisms incorporate it at low background levels. Then, in the middle of the 20th century, atmospheric nuclear weapon tests dramatically increased the amount of carbon-14 in the air. That extra signal is called bomb carbon. It is a global marker. It entered surface seawater through air-sea gas exchange. From there, it became part of the biosphere. Phytoplankton living near the surface fixed this carbon during photosynthesis. They built bomb carbon into their tissues. Then they died, were eaten, or excreted waste. Marine snow carried the resulting organic particles downward. Carcasses sank, fecal pellets sank, detritus drifted down through the water column. Each of those pathways moved bomb carbon away from the surface. A study published in 2019, with samples collected in 2017, examined Hadal amphipods from 3 Pacific trenches: the Mariana Trench, the Musau Trench, the New Britain Trench. Amphipods are scavenging crustaceans. They are abundant in trench environments. Some of the samples came from depths approaching 11,000 meters in the Mariana, near full ocean depth. The researchers measured carbon-14 in amphipod muscle tissue and in their gut contents. The result was clear. Amphipod muscle contained bomb radiocarbon signatures. Gut contents resembled surface-derived organic material. Bomb carbon, produced by mid-20th century human activity, had reached scavengers more than 10 kilometers below the surface inside about 6 decades. The contrast with the deep ocean water circulation is important. Pure water mass mixing through the deep ocean can take hundreds to 1,000 years for a full overturning. If bomb carbon were moving only by water mixing, it would barely have arrived in trench tissues yet. The food web acts as a shortcut. Sinking organic particles carry the signal far faster than the water that surrounds them. Mainstream interpretation reads this as direct evidence that rapid sinking food webs deliver bomb carbon to Hadal organisms. The historical research framing treats bomb carbon as an accidental tracer experiment for the entire ocean. A globe-spanning isotope label nobody intended to release, but every laboratory now uses. A more speculative reading suggests that trench food webs may recycle surface signals faster and more selectively than current models assume. That last point is open and being studied. The trench was once imagined as sealed off from the surface, isolated, disconnected. Carbon-14 ended that picture. The deepest place on Earth carries the chemical fingerprint of the same atmosphere we breathe, and once the door between surface and trench is open in one direction, it is open for everything else as well. Number 6. The microplastic stratigraphy of Hadal sediments. Future geologists may identify the present age by plastic fibers in trench mud. That is not a slogan. It is a working hypothesis based on what is being measured at the seafloor right now. Hadal microplastic contamination is well documented. Trenches have been confirmed as sinks for microplastic particles. Water and sediment from the Mariana Trench, including the Challenger Deep area, have been reported to contain measurable microplastic. Microplastics have been recovered from environments ranging from approximately 4,900 meters to 10,890 meters in depth. Exact claims about clean stratigraphic layers, layer by layer, need careful wording. The contamination is real. The fine resolution sediment record is still being refined. Particle types are dominated by fibers. Most fibers trace back to clothing, fishing gear, ropes, and synthetic textiles. Identified polymers include nylon, polyethylene, polyamide, polyvinyl chloride, rain, and lyocell, among others. Polymer identification relies on spectroscopy, where the chemical signature of each polymer is measured directly. The transport pathways are the same ones that carried bomb carbon. Marine snow packages plastic together with organic particles. The combined aggregate sinks faster than clean plastic would alone. Trench topography matters too. V-shaped trenches funnel sediment, carcasses, and pollutants downslope toward the trench axis. Turbidity currents, which are essentially underwater landslides of suspended sediment, can bury plastic rapidly inside trench basins. Once buried, cold temperatures, total darkness, and high pressure may slow degradation, preserving plastics for long periods. Biology connects the picture. Amphipods ingest microplastics at depths down to 10,890 meters. One multi-trench study found particles in more than 70% of examined amphipods. The animals themselves are eating the contamination. The mainstream framing reads this as the result of sinking particles, ocean currents, and biological transport pulling synthetic material downward into geographic low points. The historical research view positions the Anthropocene as a thin synthetic layer that will appear in global sediments. A more speculative reading argues that trenches may become long-term plastic archives more stable than continental dumps, because the surface above them never gets churned by erosion or human disturbance. The lost knowledge angle here is direct. Society discarded plastic as temporary trash. Trenches preserve it as a permanent record. The trench floor is not empty mud. It is a ledger, and the entries are being written in polymer fibers. And those fibers are not the only modern signature accumulating down there. Number 7. The Mariana Persistent Organic Pollutant Reservoir. The Jameson 2017 study. Amphipods from the Mariana Trench have been found carrying chemical traces of factories they never came near. The anchor study is Jameson and colleagues published in 2017. It reframed the trenches as chemical traps for industrial pollution. The contaminants in question are persistent organic pollutants, abbreviated as POPs. The defining feature is in the name. They persist. They resist environmental breakdown. They accumulate in living tissue. The two main contaminant classes in the study were polychlorinated biphenyls, or PCBs, and polybrominated diphenyl ethers, or PBDEs. PCBs were used widely in electrical equipment, in coolants, in transformers, and in a long list of industrial systems. Most of those uses have been banned for decades, but the molecules remain in circulation. PBDEs were used as flame retardants in consumer and industrial products. They share the same general behavior. They are hydrophobic. They do not dissolve well in water. They prefer to bind to fats, to particles, and to organic matter. That preference shapes their journey. Dead organisms carry pollutants with them as they sink. Fecal pellets carry pollutants. Plastics carry pollutants. Detritus carries pollutants. Anything organic that descends into the deep ocean is potentially a pollutant courier. Once on the trench floor, scavenging amphipods feed on contaminated carrion. They bioaccumulate the chemicals over time. Smaller individuals concentrate small loads. Older or larger individuals can concentrate larger loads. The Jameson study sampled the Mariana Trench and the Kermadec Trench. Samples came from depths greater than 10,000 meters in some cases. The Mariana result was striking. PCB concentrations in amphipod tissue were among the highest ever measured in marine organisms. Public summaries often compare the levels to those reported in crabs from heavily polluted Chinese rivers, with figures suggesting the trench amphipods carried roughly 50 times the concentrations of those river crab samples. The careful phrasing for any single number is that the Mariana animals were among the most contaminated marine animals measured, rather than the single most poisoned animals on the planet. The toxic concern is not abstract. POPs can affect reproduction, development, immunity, and nervous system function. Levels this high inside a remote ecosystem raise questions about long-term effects on the species at the base of the trench food web. The mainstream theory traces the pollution to global atmospheric and oceanic circulation, combined with sinking particles, building up a Hadal POP reservoir over time. The historical research framing treats the trenches as the hidden endpoint of 20th century industrial chemistry. The ban does not erase the molecules, it only stops new production. A more speculative reading suggests that Hadal animals may concentrate unknown pollutant mixtures that have not yet been targeted by analytical chemistry. That is plausible, but not yet confirmed. The deepest creatures on Earth are not isolated relics. They are chemical witnesses to industries that operated thousands of kilometers above them, and the trench has stored more than chemicals. It has also stored the energy of one of the largest earthquakes in modern history. Number 8. The Tohoku 2011 megathrust slip plain. On March 11, 2011, a fault inside the Japan Trench ruptured. The earthquake reached approximately moment magnitude 9.0 to 9.1. The setting is one of the classic subduction zones on Earth. The Pacific plate slides beneath northeastern Japan at the Japan Trench. Strain accumulates as the plates lock together. When the lock fails, the seafloor moves. What made Tohoku scientifically shocking was not just the magnitude, it was where the rupture happened. The shallow segment of the fault near the trench slipped dramatically. Shallow fault movement near the trench exceeded 50 meters. Some estimates place the movement around 50 to 60 meters of slip, among the largest directly measured megathrust displacements. The full rupture extended along several hundred kilometers of the plate boundary, often summarized as approximately 400 kilometers in length. The technical chain of events is straightforward to describe. The fault slipped suddenly. The seafloor uplifted and shifted. That displacement pushed water above it. The displaced water radiated outward as a tsunami, a long-period wave that grew steeper as it approached shallower coastal water. The wave overwhelmed coastal defenses. More than 18,000 people were killed or left missing. The tsunami also overwhelmed the seawalls at the Fukushima Daiichi nuclear plant, knocking out cooling systems and triggering a nuclear disaster. Before 2011, shallow segments of subduction zones were often considered less likely to produce huge seismic slip. The deeper, more locked portions of the fault were treated as the main earthquake generators. Tohoku challenged that assumption directly. The shallow plate boundary moved more than the previous models predicted. Drilling followed the earthquake. The Japan Trench Fast drilling project, known as JFAST, drilled across the fault to investigate. One target was friction. By measuring the residual heat left along the fault from the sliding event, scientists could estimate how much friction the fault had during rupture. The result indicated low friction and a large stress drop. The fault gave up its accumulated stress quickly and easily once it started to move. The material clue was equally important. The plate boundary was localized in a thin layer of weak smectite-rich clay. Smectite is a clay mineral that can slide easily under the right conditions. The structure was not a wide crush zone, it was a narrow lubricated band. That architecture helps explain why a shallow rupture could move so far so fast. The mainstream theory ties these strands together. Weak clay plus accumulated stress allowed enormous shallow rupture. The historical research framing treats 2011 as the moment that forced tsunami science to revise its assumptions about trench edge slip. Coastal hazard maps had to be redrawn. A more speculative reading suggests that rare clay lubricated patches may behave like hidden seismic accelerators in other trenches around the world. That hypothesis is being tested through similar drilling projects elsewhere. Comparable subduction systems include Cascadia along the Pacific Northwest of North America, the Chilean margin where great earthquakes struck in 1960 and 2010, the Sumatra margin where the 2004 event occurred, and the Alaska margin where the 1964 earthquake struck. Each margin has its own slip history. Each one is now being reevaluated with the lessons of Tohoku in mind. The hazard had not been unknown. Japan had a long tsunami history. What was underestimated was the shallow slip potential. Modern hazard models now pay closer attention to that part of the fault. The trench is not just a deep place, it is a loaded mechanical boundary where friction can fail catastrophically. 8 hidden things have been laid out so far. They sound like very different stories. A microbial mat, an acoustic recording, 2 lost robots, a chemical volcano, a radioactive isotope, a plastic record, an industrial pollutant reservoir, a megathrust earthquake. The next question is whether they share an underlying logic. Why trenches concentrate the unwanted things? A trench is a long, narrow, steep-sided depression formed at a subduction zone. The Hadal zone, which is the depth class associated with trench environments, generally ranges from 6,000 to 11,000 meters. The shape of a trench is not incidental. It is the entire reason trenches behave as collectors. Topography funnels material downslope. Sediment slides, turbidity currents, and gravity flows all move debris toward the trench axis. Anything loose on the trench walls eventually has a path downward. Organic matter sinks from the surface as marine snow. Larger carcasses, including whales, deliver pulses of food and chemicals to scavengers. Plastics attach to organic particles and sink faster than clean plastic alone. Pops bind to fats and particles, so the food web becomes an efficient delivery system. Bomb carbon followed plankton to detritus to amphipod pathways. Earthquakes can remobilize sediment and bury materials rapidly. Each input has its own physics, but they all end in the same place. Early oceanography treated trenches as remote and isolated. They are isolated in the sense of human access. They are not isolated in the sense of matter flow. The phrase that fits is vertical conveyor belt. The conveyor moves biology, chemistry, and geology together into one of the lowest topographic spots on Earth. This conveyor explains why so many separate stories converge on the same setting. Bomb carbon, persistent organic pollutants, microplastics, amphipod tissue, sediment cores, lost vehicles, and earthquake records all share the same gravitational and hydrodynamic logic. Mainstream theory frames trenches as passive sinks driven by gravity and topography. The historical research view treats each new sampling expedition as adding another human fingerprint to the deep record. A more speculative framing suggests that trenches may preserve a more complete Anthropocene archive than continental shelves, because the trench environment is undisturbed by erosion and burrowing. The phrase away does not describe a real place inside an ocean system. Anything dropped into the surface ocean has a non-zero probability of arriving at the trench floor. So the practical question becomes how scientists actually reach a place that punishes equipment and people equally. How scientists see what cannot be reached. Pressure increases by roughly 1 atmosphere every 10 meters of seawater. At Hadal depths, pressure exceeds 1,000 atmospheres. Humans cannot casually visit a place like that. Every direct observation requires hardware that was designed and tested specifically to survive the trip. Crude submersibles provide direct human observation, they allow sample selection in real time, they have limited bottom time and limited mobility. Remotely operated vehicles provide manipulators and high-quality cameras, but they depend on a continuous tether to a surface ship. Autonomous underwater vehicles travel without a tether. They carry their own batteries and computers. Their decision-making is bounded by the software they were programmed with. Free-fall landers are some of the most productive trench tools. They drop to the bottom under their own weight, carry bait to attract scavengers, collect samples, and then release ballast on command to float back to the surface. They are simple, robust, and easier to deploy in numbers than a deep submersible. Many of the amphipod studies described earlier rely on lander work. Listening tools are equally important. Hydrophones detect events that no camera will ever record. Earthquakes, ice breakup, volcanic activity, whale calls, human shipping. Each has a recognizable signature. Sediment cores preserve layered records of particles, pollutants, and earthquake-driven deposits. Boreholes, like ocean drilling. Program Hole 1200C sample deep fluid systems directly. Isotope laboratories detect carbon-14 at concentrations invisible to cameras. Spectroscopy identifies plastic polymers down to specific chemical bonds. Gas chemistry instruments identify methane, hydrogen, and reduced fluids. Temperature probes measure frictional heat after earthquakes. Older expeditions relied on dredges and indirect sampling. The bucket on a wire was, for a long time, the basic tool. Modern trench science combines robotics, chemistry, genetics, and geophysics. The mystery often persists because cameras see surfaces while chemistry explains causes. A microbial mat looks like color until somebody runs a sample. A descending tone sounds like a creature until somebody maps the ice nearby. Mainstream interpretation in trench research depends on multi-instrument missions. Each instrument constrains a different part of the puzzle. A speculative angle, increasingly serious as the technology matures, holds that future artificial intelligence-guided samplers may recognize unknown life forms or chemistry in real time and adjust their sampling on the fly. That is no longer pure science fiction. Pieces of it are already being tested. Exploration advances when tools translate pressure, darkness, and silence into measurable signals. And once those signals start coming back, the basic question changes from what is down there to what feeds it. Chemosynthesis, serpentinization, and life without sunlight. The central biological question raised by trench observations is direct. What feeds life where sunlight cannot go? The answer is chemosynthesis. Chemosynthesis is biological energy production from chemical reactions instead of from light. It contrasts with a photosynthesis, which depends on sunlight and supports surface ecosystems by converting solar energy into organic carbon. Reduced chemicals can store usable energy. Hydrogen is one. Methane is another. Sulfide is another. Iron in its reduced form is another. Microbes that can oxidize these molecules effectively run the energy economy of certain deep environments. Larger animals tap into that economy by hosting symbiotic microbes inside their tissues or by grazing on microbial mats. Serpentinization is one of the most important reactions in this story. When seawater reacts with ultramafic rock, the products include serpentine minerals, brucite, hydrogen gas, and alkaline fluids. Hydrogen can feed microbes. Methane production can occur as well, depending on local conditions. Methane in turn supports a different set of microbial mats in symbiotic animal communities. Extreme pH selects for specialized microorganisms. The community that can live at pH 12 is not the community living in normal seawater. This is the framework that makes the Sirena Deep yellow mats biologically interesting. They may represent one form of deep chemical ecology, even if the metabolism is not yet identified. South Chamorro is a clearer example of alkaline chemical energy because the chemistry has been sampled directly. Color matters in the field because yellow, white, black, and orange deposits often hint at specific chemistries. White can suggest brucite or carbonate. Yellow can suggest sulfur. Black can suggest sulfides. Color also misleads because lighting and minerals can imitate biology. The pivotal moment in this field came in 1977. The discovery of hydrothermal vent ecosystems at the Galapagos Rift demonstrated that complex animal communities could thrive on chemical energy rather than sunlight. Tube worms, vent crabs, and dense microbial mats appeared in places that the standard model said should be empty. Trench science now asks whether similar systems exist deeper or colder in places without obvious magmatic heat. Mainstream theory holds that chemosynthesis supports localized trench life wherever fluids leak, vents emerge, or organic falls accumulate. The historical research view positions trenches as containers for overlooked analogs of vent ecosystems, hidden in places that did not get systematic attention until the past 2 decades. A more speculative framing draws comparisons to early Earth before photosynthesis evolved, and to icy moons like Europa and Enceladus, where rock and water may meet beneath ice shells. Life innovates by exploiting imbalance. Where rock, water, and chemistry are not at rest, biology has a chance to establish itself. The trench is one of the places that imbalance can persist for very long periods, and that imbalance is now overlapping with another set of signals, the signals humans put into the ocean themselves. The human fingerprint at full ocean depth. 3 traces define modern human presence in the deepest trenches: bomb carbon, plastic fibers, banned industrial pollutants. Each is a different category of fingerprint. Carbon-14 is an isotopic fingerprint. Microplastic is a physical fingerprint. PCBs and PBDEs are chemical fingerprints. Each begins at the surface or on land. Each enters the ocean through different pathways. Each reaches depths once assumed isolated. Particle association makes pollutants and plastics sink. Hydrophobic chemicals bind to fats and particles. Synthetic polymers attach to marine snow. Once bound, downward transport becomes likely. Biological activity then concentrates everything inside animals. Feeding accumulates chemicals. Geological activity buries the result. Sediment burial preserves traces in mud, sometimes for very long periods. The 3 fingerprints differ in what they reveal. Carbon-14 reveals time scale. The signal moved from atmosphere to trench animals in decades, not centuries. That is faster than the deep ocean water itself moves through circulation. Pops reveal persistence. Banned chemicals remain mobile years after their production ended. Plastics reveal material durability. Synthetic polymers do not break down quickly under cold, dark, high-pressure conditions. Industrial civilization treated the ocean as dilution space for a long time. The assumption was that the volume of seawater would dilute any pollutant to insignificance. Modern measurements at the trench floor show concentration instead of disappearance. The geometry of the ocean does not dilute everything equally. Some places trap material, some places preserve it. Mainstream theory ties global circulation and sinking matter together as the connection between surface pollution and trench accumulation. The historical research view treats the Hadal zone as an archive of industrialization, a record of which chemicals were used in which decades. A more speculative framing suggests that unknown synthetic compounds, products that have not yet been targeted by analytical chemistry, may already be buried in trench sediments and waiting to be detected. The deepest seafloor records civilization through chemistry, not monuments. There is no plaque. There is just a layered signal of what humans made and where it eventually came to rest. Reaching that record, however, requires fighting the same physical environment that produced it. Pressure as the hidden villain. Pressure is the constant factor across every trench story. At 10,000 meters of depth, pressure is roughly 1,000 times surface atmospheric pressure. The number is easy to write and difficult to feel. Pressure crushes air-filled spaces instantly. Any container of trapped gas at that depth has to be either rigid enough to hold or collapsed by design. Human bodies require pressure vessels to survive there at all. Engineering responses are specific. Electronics are placed in oil-filled housings, where the surrounding fluid transmits pressure equally and prevents collapse of sensitive components. Ceramic spheres provide buoyancy at depth. Titanium alloys provide structural strength. Syntactic foam, made of hollow microspheres in a resin matrix, provides flotation that does not crush. Nereus's likely implosion shows how a small flaw can become fatal. A microscopic weakness in a glass sphere, a poor weld, a sealing surface that was not perfectly cleaned during assembly, any of these can become the failure point at 16,000 pounds per square inch. Kaiko's cable failure shows that pressure also works indirectly through material fatigue. The cable did not implode. It was worn down by repeated cycles of bending, tension, pressure exposure, and contact with seawater. Biology adapts in its own way. Hadal amphipods carry pressure-tolerant enzymes with structures that remain functional under conditions that would denature similar proteins from shallow species. Their cell membranes are tuned to remain fluid at high pressure and low temperature, where surface organism membranes would become rigid. The molecular details are still being mapped, but the general pattern is clear. Life has had a long evolutionary runway to refine these adaptations, with deep-dwelling lineages building on small advantages over millions of generations. Sampling problems multiply at depth. Organisms may rupture or change during ascent as gas-filled structures expand. Chemical samples can shift phase or concentration as pressure drops. Fragile biofilms can be destroyed by the thrusters of the very vehicle sent to study them. Sediment cores can smear layers during recovery. Every recovery operation is a small race against equilibration. Deep-sea exploration advanced when materials science improved. The history of trench science tracks the history of pressure-resistant materials. Early dives used steel hulls. Modern hulls use forged titanium with carefully engineered weld geometry. Pressure chambers on land now test instruments to expected operating depths and beyond, before any expensive vehicle is risked at sea. Many failed dives left no recoverable evidence at all, which means lessons came from the few wrecks that produced visible debris or shifted telemetry. Mainstream theory frames pressure as the main engineering barrier to Hadal science. The historical research view holds that each lost vehicle has improved later designs, even when the loss itself yielded no return. A more speculative angle considers whether pressure may allow unknown biochemical strategies in trench microbes, with reaction kinetics or molecular folding pathways that only function under Hadal conditions. Pressure is not a backdrop. It is a physical law that edits what humans can know. And it is also one of the ingredients that makes trench earthquakes so dangerous. Trench earthquakes and the surface world. Subduction zone trenches store enormous amounts of elastic strain. The two plates are locked together along a contact surface. Tectonic motion continues at a steady rate of centimeters per year. Strain builds in the rocks on both sides of the locked patch. When friction fails, the patch slips, and the seafloor can move suddenly. The paradox of trench earthquakes is that the rupture begins offshore, but the disaster arrives on land. Vertical seafloor displacement creates tsunami waves. Shallow slip near the trench is especially dangerous for tsunami generation because it directly lifts a large column of water near the source. Tohoku in 2011 proved that shallow segments can slip more than expected. Smectite-rich clay along the plate boundary can reduce friction and allow more displacement during a single rupture. Drilling temperature measurements after a rupture can estimate the friction at the time of slip. Post-seismic creep and after-slip continue the story for months or years afterward, with smaller adjustments along the fault. Each measurement tightens the model. Japan had a long history of tsunami events going back centuries. The 2011 earthquake exceeded many planning assumptions. Comparable margins include Sumatra, where the 2004 earthquake produced a basin-wide tsunami. Chile, where the 1960 rupture produced a magnitude near 9.5, and the 2010 event produced another major earthquake. Alaska, where the 1964 event was the largest North American earthquake of the modern instrumented record. Cascadia, where paleoseismic evidence points to a major rupture in 1700. Each setting has its own slip behavior. Modern relevance is direct. Coastal hazard maps must consider worst-case trench slip scenarios, not only the average. Warning systems can detect earthquakes within seconds, but near-field tsunamis can reach the coast before warnings can be processed and acted upon. Infrastructure choices matter. Seawall heights, evacuation route planning, nuclear plant siting, and building elevation all interact with the worst-case scenario. Ancient tsunami deposits can be forgotten until repeated. Sand layers preserved in coastal marshes record older inundations, sometimes hundreds or thousands of years old, until a new event arrives and overlays the old record. Mainstream theory ties Tohoku's rupture to plate locking and sudden release. The historical research view holds that paleo-tsunami records may reveal older analogs, events that occurred before the instrumented era. A more speculative framing suggests that some trench patches may behave as rare superslip zones, capable of unusually large single-event displacements. The trench floor can move once. Millions of people inherit the consequences. Final synthesis. The deepest trenches as archives, engines, and warnings. The trenches are archives. They store carbon-14, microplastics, persistent organic pollutants, sediment layers, and the wreckage of dead machines. They are engines. Serpentinization, chemosynthesis, earthquakes, and fluid flow continue in darkness regardless of whether anyone is watching. They are warnings. What humans discard or underestimate eventually returns, as evidence somewhere measurable. Sirena Deep showed visible mystery at biological limits with structures observed but not sampled. The slowdown showed the ocean's acoustic scale and the danger of premature mystery claims, where iceberg grounding explains a sound that once sounded supernatural. Keiko and Nereus showed that exploration tools can become artifacts, lost to the same environment they were built to study. South Chamorro showed life built from water rock chemistry, sustained without sunlight. Carbon-14 showed that the Cold War reached the Hadal food web within decades. Microplastics showed modern trash entering geological time. Persistent organic pollutants showed banned chemicals surviving through food chains. Tohoku showed that hidden trench faults can become surface catastrophes that kill thousands. The deep sea moved from myth to measurement only recently. Most of the data described here post-dates the 1960s. Some of it post-dates the year 2000. Every story depends on pressure, gravity, chemistry, and time. The trench is the place where those four variables converge most strongly. Modern science replaces mystery with instruments. It does not always replace mystery with certainty. Each expedition revises the idea of isolation. Each new sampling technique changes the inventory of what is down there. Mainstream theory ties trenches to the surface through physical and biological pathways. The historical research view tracks how each generation of expeditions has revised the picture. A more speculative framing suggests that the Hadal zone may still hold unknown life strategies and chemical archives that have not yet been sampled. What is hidden is often hidden by access, not by conspiracy. The trenches are 11 kilometers deep, dark, cold, and crushing. They are not concealing secrets. They are simply hard to reach. The sinister element of these 8 stories is not a monster. It is the steady accumulation of evidence that the deepest place on Earth is connected to everything humans do above it, and that the laws of physics and chemistry quietly file every piece of that evidence away in the same low place. The deepest trenches are not empty ends of the Earth. They are where natural laws quietly collect the evidence.